We've been looking at electrical events in the heart. Let's look at mechanical events. The cardiac cycle. Cardiac cycle is all the events associated with blood flow through the heart during one complete heartbeat. All right. We have what's called systole and diastole. Systole is when the heart contracts. Diastole is when the heart relaxes. All right. So remember, the heart, in order to pump, we have to contract to pump blood out, and then there has to be a relaxation period when the blood can flow back in. So that's what's going on. Systole is contraction. That's when blood is being pumped out. Diastole is relaxation. That's when blood is flowing back in again. Let's look at phases of the cardiac cycle. So ventricular filling takes place in mid to late diastole. So in other words, while the heart is resting, the ventricle is filling with blood. The AV valves are open. Remember, AV valves are normally open. As blood comes back into the atria, the blood is simply trickling down through the open AV valves into the ventricle, all right? 80% of blood passively flows into the ventricles, all right? So in other words, as blood is returning from your lungs and from your body, it's returning either into the right atrium from your body or into the left atrium from your lungs. That blood is just flowing in and then just trickling through the open AV valves down into the ventricle. That's the way 80% of the filling of the ventricles takes place. Then atrial systole occurs. That's when the atria contract, all right? That delivers the remaining 20%, all right? That last bit gets pumped and actually physically forced down into the ventricle. At that point, we have what's called the end diastolic volume. Volume of the blood in each ventricle at the end of ventricular diastole, all right? We had atrial systole, it's true, but the ventricles have not contracted yet. The ventricles are still in diastole, all right? The EDV, think of that as the total amount of blood that is available for your heart to pump, okay? So in one ventricle, the total amount of blood that's in there at the end of diastole, at the end of the relaxation phase, that's the most blood that your heart can possibly pump on the next beat. That's EDV, end diastolic volume. That means your heart is full. Is your heart full? My heart is certainly full. So when your heart is full, that's end diastolic volume. AV valves are open most of the time, remember, allowing blood to trickle down through the atria, slowly filling the ventricles. Okay, what happens next? Now we have ventricular systole, contraction. The atria relax, ventricles begin to contract. Rising ventricular pressure results in closing of the AV valves. Remember, it's like grabbing that toilet paper tube in the middle. When you squeeze it, it's going to make stuff try to come out both ends. Well, the valves are on one end, and so when stuff comes out of the one end of the toilet paper tube, it's going to force the valves to shut. They're going to slam shut because the ventricle contracts pretty hard. So those AV valves slam shut from the force of the blood. We have an isovolumetric contraction phase during which all valves are momentarily closed. Then in the ejection phase, which happens next, the ventricular pressure exceeds the pressure in the large arteries. That forces the SL valves open, all right? So the AV valves were normally open. When the ventricle contracted, that slammed them shut, and then the force of the blood then going through the other end of the toilet paper tube, that forces the SL valves open. Blood now flows into the pulmonary trunk and into the aorta. Stroke volume is the volume of blood pumped during ventricular systole. All right, so remember we had end diastolic volume. That was the full amount. That's when the heart was completely full. Now the stroke volume is how much of that we now pump out. And you're thinking, wait a minute, don't we pump it all out? No, under normal circumstances we don't. When you're at rest, you don't need a lot of blood being pumped. You're not working very hard. So the ventricles normally only pump some of the blood out, all right? And that amount is called the stroke volume. Now, as you exercise, as you run, if the chupacabra is after you and you're running, your heart starts working faster, the contractility goes up, you're going to start pumping more blood out. Stroke volume will go up under stress, when you have to. But normally we don't pump all the blood out. So stroke volume is going to be less than EDV. The total amount of blood that was in there when the heart was full, we only pump part of that out. The part that we pump out is called the stroke volume. And then there's going to be some left over, right? That's called the end systolic volume. So how much is left after we pump some out? So of the EDV of the total, we pumped out some of it. That was the SV, the stroke volume. And then we have some left over. That's the ESV, the end systolic volume, the amount that's left over after ventricular systole. Okay? So isovolumetric relaxation occurs in early diastole, then the ventricles relax. Backflow of blood in the aorta and pulmonary trunk closes the SL valves. So during ventricular systole, we force those SL valves open, we force blood out, and then, like, remember in the aorta, some of the blood will make it over the hump, but the rest of the blood won't, all right? It's going to fall back down. When it falls back down, what happens? It shuts those SL valves. And we're now at the end of the cardiac cycle. This causes what's called the dicrotic notch, a brief rise in aortic pressure. That's not really critical. I'm not going to ask you about that, I promise. That graph, by the way, looks complicated. It would behoove you. That's a neat word, isn't it? Behoove. It would behoove you to go through that. Look it up on the top. It shows you the ECG. Then it shows you the heart sounds. Then it shows you what's happening with pressure, shows you what's happening with volume, and it shows you for the valves whether they're opened or closed. That is an incredibly just informative graph. And I seriously recommend that you sit down and take 10, 15 minutes and check that graph out, because it will really greatly improve your overall understanding of what's happening during a cardiac cycle. So the heart sounds, you've heard your heart. You've listened to your heart. Your heart goes ba-bump, ba-bump, ba-bump. We don't say ba-bump. They use different terms. They use lubbed up, which, sounds lubbed up. Sounds like, before, I'm going to the rally, I'm going to get lubbed up before I get there. No, I don't know what that even means. Lub is the first heart sound. Dup is the second heart sound. Lub, dup. All right? So what makes those sounds? It's the closing of the valves, believe it or not. That's what does it. When the valves close, that makes a noise that you can hear. So the first sound occurs as the AV valves close, all right? So that's when the ventricle contracts. Remember, the blood flowing back, trying to get back through the valve, slams the valve shut. That makes the first sound. That's the lub. That's as the AV valves close. The second sound is, remember, some of that blood didn't make it over the arch, and it comes back down and hits those SL valves. They slam shut, and that's the second sound. That's dup. So that's what it is. When you hear the sound of your heart beating, when you feel it, you're feeling the valves slamming shut, all right? There's a lot of force in that heart muscle. Those valves really slam shut, okay? Heart murmurs are abnormal heart sounds, most often indicative of valve problems, all right? So regurgitation. If the valve isn't closing completely, then blood will regurgitate back into the previous chamber, and that makes a little murmuring sound if you're listening through a stethoscope. And by the way, I'm sure you've had somebody listen to your heart with a stethoscope. You've been to the doctor at least once in your life, haven't you? Or a nurse? Notice how when they listen to your heart, they put the stethoscope there, and then they move it, and they listen a little bit, and then they move it, and they listen a little bit, and then they move it. What are they doing? They're actually listening to your 4 heart valves. And nurses are taught where to do this. So for the aortic valve, you listen at the second intercostal space on the right sternal margin. Pulmonary valve, second intercostal space at the left sternal margin, and so on. So that's what their nurses or doctors are doing, or the medical assistant, whoever. As they listen to your heart, they're moving the stethoscope, trying to listen to the 4 valves, and they're listening carefully to each one in case they hear a murmur, which might therefore indicate a valve problem, okay? See, they actually know what they're doing. How about that? And here, oh my gosh, what a wonderful, wonderful diagram showing basically the atria, the ventricles, the AV valves, the semilunar valves, atrial systole, then early ventricular systole, late ventricular systole, and so on, showing exactly what's going on inside the heart with respect to the chambers and with respect to the valves and so on. Once again, seriously, take 10 minutes. Go over that diagram. It will help clear up any ambiguities you have. If you follow that diagram through, that is so wonderful. It explains everything so incredibly well. All right, which of the following statements is false? The T wave corresponds to ventricular repolarization. The second heart sound corresponds to closing of the AV valves. Most ventricular filling occurs passively. Contraction is also known as systole. ESV is the volume of blood remaining in the ventricle after ventricular contraction. Once again, you really have to know this stuff through and through. These are the kinds of questions I will put on quizzes and exams. You need to know everything well enough that you can easily spot which 4 of those are true and which one of those is wrong. And it's that one. The second heart sound is the closing of the SL valves. It was the first heart sound that was the AV valves. Okay? Now we get on to the start of your journey through hell. No, now we're actually going to start using some numbers. Is that cool or what? Oh my gosh. We're going to look at basically how to measure how well all of this is going, how much blood is moving, all right? So let's start talking about cardiac output. This is a fundamental measure that gives a lot of information about the heart. This is the volume of blood pumped by each ventricle in 1 minute, okay? So how much blood, remember you got a heart rate of 75 beats per minute. So after 1 minute, your ventricle will have beat roughly 75 times. So all 75 of those will have moved out a total amount of blood. So how much blood does each ventricle pump in 1 minute? That's called your cardiac output, okay? Now, cardiac output is equal to heart rate times stroke volume. Think about it. Your heart rate is beating 75 times per minute on average. Stroke volume, remember, is how much blood you pump out with every beat. So if you take the total number of beats and multiply that by the volume for each beat, you're going to get the total amount of blood pumped. Look at that left diagram. Look underneath those little, rectangles with the red and everything. Cardiac output is on the far right. Notice how that's measured. Milliliters per minute. Milliliters is a measure of volume. That's how much blood. Minute is a measure of time, right? Then move to the left. Look, stroke volume. How do we measure stroke volume? That's milliliters per beat, right? How many milliliters do you pump out with every beat of the heart? Then, all the way over to the left, your heart rate, of course, is in beats per minute. Now take a look at what happens when you multiply heart rate times stroke volume. You have beats per minute times milliliters per beat. Remember doing this like in 4th grade or whatever? Notice how beats are going to cancel. So what are you going to end up with? Milliliters per minute. So notice, over on the left again, normal heart rate would be about 75 beats per minute. Notice then stroke volume, typical stroke volume would be 70 milliliters per beat, okay? When you multiply those together, you get 5,250 milliliters. Now remember, that's milliliters. Milliliter is 1,000th of a liter. So how could we convert that then to liters? All we have to do is move the decimal point 3 places to the left. So what's that going to be? That's going to be 5.250 liters. So in other words, a typical cardiac output is around 5 liters per minute. Does the number 5 liters sound familiar? Have we worked with the number 5 liters before? We have. Remember, that's roughly how much blood you have in your body. Typical person has around 5 liters of blood. Remember, females typically, 4 to 6, males, 5 to 7. Females 4 to 5, males 5 to 6. On average, 5. So what does that mean, therefore? You have a total of 5 liters of blood in your body. Your cardiac output is 5 liters per minute. So what does that mean? It means basically that you pump your entire blood supply completely through your entire body once every minute. If you were to, put a little tag on an individual red blood cell, that red blood cell would travel completely through your entire body once every minute, all right? So 5 liters, both cardiac output and your total blood volume. So heart rate, beats per minute, stroke volume, volume of blood pumped out with each beat, okay? That makes cardiac output. So resting cardiac output, this is what I just did. That's milliliters per minute. If we multiply that times typical heart rate, 75 beats per minute, times typical stroke volume, 70 milliliters per beat, notice the beats are going to cancel, and we get liters per minute. If we convert it to liters, if we left it as milliliters, it would be 5250. You're going to have to do some problems like this for your homework, and also on quizzes and exams. I'm going to have you do problems. There's actually going to be some arithmetic on your quizzes and exams. I highly recommend that you work in milliliters. You can work in liters if you want to, but a lot of people I've noticed seem to have trouble with decimal points. So I'm going to recommend that you work in milliliters, and I think that'll make it easier. But listen, this is the United States of America, damn it. You can do it either way you want to. I'm just recommending. So the normal cardiac output then resting is 5 liters per minute. When you're sitting there right now just farting and thinking about sex, you're pumping about 5 liters of blood per minute. Maximal cardiac output is 4 to 5 times resting cardiac output in non-athletic people. So when the chupacabra comes through the door and you have to start running and fighting, you can go up to 4 to 5 times that amount, which would be 20 to 25 liters per minute. You'll be pumping your entire blood supply through your body 4 to 5 times in 1 minute. Maximal cardiac output may reach 35 liters per minute in trained athletes. People like Lance Armstrong, that son of a bitch, that cheater, but all the other cyclists were cheating too. He's one of the most phenomenal athletes in the history of planet Earth. He actually truly is. And in particular, his cardiovascular system is absolutely amazing. They've done studies on his cardiovascular system because it's so amazing. It's so extraordinary. But yeah, he can be pumping 35 liters per minute. His entire blood supply 7 times through his body at maximum output. Now, cardiac reserve is the difference between resting and maximal cardiac output. Reserve means kind of like how much do you have for a crisis, okay? You normally pump 5 liters per minute. If you can pump 30 per minute in a crisis, well, then you have a reserve of 25 liters, all right? Remember, typical blood volume is about 5 liters. Therefore, at rest, an individual red blood cell will make a complete circuit through the body about once every minute. Damn, is your heart amazing or what? The answer is yes.